All right, cool. So for this one, they're giving us all the clues that we need. All right, so this is theta lives in quadrant 1, and they want us to find cosine of theta if tangent of theta is this. So now remember, katoa is the mnemonic device. That's a fancy word for a thing that helps us to remember. Katoa. And what it really means is that sine of theta is equal to the opposite over the hypotenuse, cosine of theta. And theta is just a Greek letter that means the angle, right? Is the adjacent over the hypotenuse. And tangent of theta is equal to the opposite over the adjacent. So if I sketch this out, the xy plane is divided into 4 quadrants. And so quadrant 1 is here, quadrant 2 is here, quadrant 3 is here, and quadrant 4 is here. So that means that my little right triangle goes like this. And that point right there is my x comma y. Theta is usually right here. That's the measure of the angle. Well, this is the opposite. The hypotenuse is the leg across from the 90-degree angle, and the opposite side is across from the angle theta, and the adjacent is the third side that's left over. So we say x comma y, but really that would be the length from here to here is the x value. So this is really the adjacent value, or the value of the adjacent side, comma, the opposite. Okay, so let's unpack this. So we know that tangent of theta is equal to the opposite over the adjacent. And we're told that that is 3 root 5 all over 2. Okay. Now this is a little tricky. Not really though. So if I think of my right triangle, all right, I'm just going to sketch a bigger one out here. I'm going to get a line that goes like this, a line that goes like this. There we go, perfectly drawn right triangle. Then my opposite is equal to, now there's some simplification and some math that's going on here. That's okay. I'm just going to take the top part and say 3 root 5. Then my adjacent, which is down here, that's equal to 2. And then I have my theta, which is right here. Now I can solve for the hypotenuse by using the Pythagorean theorem. So most of the time, we're used to seeing the Pythagorean theorem written like this, where we have a squared plus b squared equals c squared, and then c squared is always the hypotenuse. Well, we could rewrite that in terms of trigonometric labels as being the opposite squared plus the adjacent squared is equal to the hypotenuse squared. So now I'm just going to plug this stuff in. My opposite is 3 root 5 squared plus 2 squared, and that's equal to the hypotenuse squared. So 3 root 5, 3 times 3 is 9. The square root of 5 squared is going to be just 5. So 9 times 5 is 45 plus 2 squared, which is 4, and that's equal to the hypotenuse squared. Now, if you ever want to double check that, we could just plug it into our graphing calculator to see if that's valid or not. So I'm just going to do that real quick, just to kind of verify where that comes from. If I say 3, the square root of 5, oops, let me clear that out. If I say 3 times the square root of 5, and then I close the parentheses, and then I square that, I should get 45. So 3 times 3 is 9, and then when you square a square root, you're just left with the base, which is 5. 9 times 5 is 45. So I just wanted to verify that. So now this is interesting. 45 plus 4 is 49, and that's equal to the hypotenuse squared. I'm going to take the square root of both of these, and I get plus or minus 7, but the hypotenuse is always positive, so this becomes 7. Well, they're asking us to figure out what is cosine of theta. Well, cosine of theta is going to be cosocatoa is the adjacent over the hypotenuse, which is going to be 2 over 7. So that's it. That's it on that one. That's how you get the answer for that one.